Yeah. So now, I don't know where this is. So now, let's begin. So last time we saw this result, I mean, and part of the proof. Yeah. So M is the set of isometries of R2, or the set of rigid motions of R2. Rigid motion. So we saw that rigid motions are isometries, meaning so rigid motion means it preserves distances, and and as a consequence, it's a bijection. Yeah, so it's like a symmetry of the plane. Yeah, and last time we saw that if you have it, so there are there are four kinds of there are broadly two kinds of um, uh, isometries. One which are orientation preserving, and one which are orientation reversing. Yeah. So orientation preserving means you don't flip the plane. Yeah, you just keep the plane. So it's so there are two kinds of it: rotation of the plane by an angle theta about some point, and translation by a vector. Yeah. So these are orientation preserving, and examples of orientation reversing is reflection by a line L. Yeah, a reflection about a line L. So you have a line in the plane, and you reflect about that line. Take any line in the plane R2 and then reflect about that line, or a glide reflection. So glide reflection means there is a reflection about a line, and then you translate not by some arbitrary vector, but a vector parallel to that line. Yeah, so you reflect like this and do this move around along that line. Yeah. So these are some examples of orientation reversing isometries, or orientation reversing rigid motion. And then the theorem is that these are, in fact, these are all the isometries of the plane. Yeah. So every rigid motion is of the above type. And we saw that, so what we saw last time is part A is true. So that is, if we take any orientation preserving rigid motion, then it is either rotation by an angle theta about some point, or it is a translation. So we saw that if it is not a translation, then one point is fixed, and then it has to be a rotation around that point. Yeah. So that we saw. So today I'll complete the argument showing that if it is or if it is orientation reversing, then it has to be either a reflection about a line or glide reflection. Yeah. So remember, any rigid motion we saw is either rho theta times r, where r is the reflection about the x-axis, x1 axis, if you like, and rho theta is the rotation by angle theta, or followed by a translation. Yeah. So so anything. So in this case, um, in this situation, M would look like translation followed by rho theta for some A in R2 and theta, some angle. Yeah, theta angle. So maybe it is somewhere between 0 and 2 pi. Right? So anything which is orientation preserving is of this form, and anything of which is orientation reversing is of the form M equals TA rho theta R. So there has to be one reflection. So we saw that every element in this group M, capital M, is either of this form or that form last time. Yeah. So now if we are assuming it's, we only have to look at case B, yeah, where it's orientation reversing. So M must be of this form, yeah, for some A in R2 and theta between 0 and 2 pi. Yeah. and R, remember, is the reflection about the x1 axis. Okay. So we will do this in two steps in some sense. Yeah. So case one is, suppose there is no translation. Yeah, you are translating by the zero vector. So there is no translation. A rho theta composed R. So in this case, what happens is, this is same as reflection by so reflection by x1 axis and then rotating by theta is same as reflecting by another reflecting along some other line. Yeah. So say this is your x1 axis, x1, x2, and let's say this is the angle theta. Yeah. So what happens is, if you reflect, so let's say this is theta by 2, this is the bisector. So if you think about it, if you reflect this line along x1 axis and then rotate it by theta in anti-clockwise direction, yeah, then you will get back to that same line. Yeah. So under this isometry, this line L is preserved. L is preserved by rho theta composed R. Yeah. So it fixes L, and it is actually a reflection by this. So for instance, you can check, where does x1 go? X1 should go to this line. Yeah. So under reflection, of course, x1 is preserved. Yeah, because R is R fixes x1 the x1 axis. Yeah. So by rho theta, it will go to this thing. Yeah. So so under this. Yeah, so this, I don't know why it is so thick, but okay. So it will go something like this. Yeah. X1 will go there, and you can check other lines as well. So if you take something between x1 and L, then under reflection it will come here. And if you under, so if you take a line something like this, under reflection by x1, this will first move here. Yeah. And then if you do the angle change by theta, it will come here. Yeah. Which is same as reflecting along the, so, and then here. Yeah. So this line basically goes here, which is same as reflecting along the line. Yeah. So you can visualize geometrically that this is indeed reflection along the line L. Yeah. Where L is where L is the line at an angle theta from the x-axis, theta over 2 from the x-axis. Is that okay? Yeah. So if we change the angle by so if we operate this is meaning rho theta composed as reflection by an x along x1 axis is same as reflecting by reflecting the plane along some other line L, which is this line. Yeah. Now let's do the general case. So now m equals PA rho theta R. Yeah. Then first, if you do rho theta R, then what does it become? It becomes reflection along this line L. Yeah. So if you think about the picture, then let's say A is some vector here. Yeah. And theta is this angle, and this is theta by 2. Yeah. So what? And maybe I'll draw A somewhat far away so that it's easier to draw my next move. Yeah. So what happens? These two terms rho theta composed R, what will it do? It will make sure that the reflection happens along L. Yeah. And then you are doing translation by TA. Yeah. So, so what we can do is we can change our coordinates. Yeah, we can change the basis to make sure that this is x-axis, x1 axis, and its perpendicular guy is the x2 axis. Yeah, so we can make this as the new x2 axis and L as the new x1 axis, and then try to do the translation. So if we do this change of variable, what happens is the upshot of that is we can replace rho theta r by just r. Yeah, because then we are just doing reflection along L, which is the x1 axis, and then of course now the coordinates of A, which was earlier with respect to this was some A1, A2, would become something different. Yeah, you'll have to measure this length and this length, and those will be the coordinates of A, but it doesn't matter. It will be some pair A1, A2. Anyway, we have to prove this for any A. Yeah. So the value of the coordinate of A will change, but that's about it. Yeah. So may assume theta is 0. Yeah. So we are just doing reflection followed by a translation, and that we want to show is either a reflection or a glide reflection. So in fact, we will show that it is a glide reflection. Yeah. So so in this case, so this was sort of case 2. Yeah. So maybe actually case 2 should start from there itself. Case 2 is here. Okay. So if we assume theta is 0, then we have m is TA times r. So m is TA times r for some a. So this a is different from that a, but it doesn't matter. Yeah, whatever that a is, some number a, some vector a in R2. Okay. So what does TA times r do to x1, x2? So R rotates, yeah. I mean, R is reflection. So x1 stays as it is, and x2 goes to minus x2. Yeah, that is what reflection does. And translation adds the vector a1, a2 to it. Yeah. So if you look at the composition, TA composed R, then it will send x1, x2 to x1 plus a1 minus x2 plus a2, right? So this is what m is doing as a function. This is how it looks like, and this we can show is indeed a glide reflection. So in fact, this is reflection about this is not about the line x2 equals a2 over 2. So when I was writing this, my pen wasn't writing properly. Yeah, so it is so it is reflection about a2 a2 over 2, about the line a2 over 2. So remember, now we are in this setup. Yeah. So x2, and so a is some vector here, a1, a2. So the height is a2. Yeah. So you are doing reflection. Yeah. So any arbitrary point x1, x2, you are first reflecting to get here, and then translating by a1, a2. Yeah, by this length vector. So this point will actually go to this point. So will go somewhere. Yeah. So I don't know if this looks parallel, but may not be parallel. Yeah. So so wherever it goes. Yeah. So somewhere. So the point is we will show that this is glide reflection. Yeah. So actually this should be reflection follow. Yeah, so it could be here. Yeah, that is okay. So so we will see exactly what we are doing. Yeah. So So we will show that this happens. It's reflection along the line A2 over 2. So A2 over A2 is this. So A2 over 2 should be somewhere here. So it will reflect about A2 over 2, and then you add A10 to it. Yeah. So you add A10 to it, and that is what this operation is. So I want to prove that TA dot R is precisely this. Okay. So let's check it. Yeah. So let's take any. Yeah. So I've already drawn the picture here. Yeah. So A2 is this. A2 over 2 is this. Let's say x1, x2 is this point. Yeah. Then then we want to say that this reflecting about A2 over 2 and then adding the vector A10 is same as TA comma R. That means it will give you x1 plus A1 minus x2 plus A2. Yeah. So what is reflecting about the A2 over 2? You sort of so x1 doesn't change, and x2 will become x2 minus 2d, where d is this distance. Yeah, d is the distance of x2 from this line x2 over a2, a2 over 2, right? And so d is basically this difference, x2 minus a2 over 2. Is that okay? So that is what reflection about the line x2 equals a2 over 2 looks like. Right? So it will go here, and then you add a10 to that vector. Yeah. So under reflection about x2 equals a2 over 2, followed by translation by a10. What we get is x1, x2 goes to, so you'll have to add goes to, okay. So let's do it in two steps. So goes to x1, x2 minus 2d plus a10. Yeah, this is what under this operation, x1, x2 will go to this. Yeah, but what is this? So this the first coordinate is precisely x1 plus a1, and the second is d is x2 minus a2 over 2. So 2d is 2x2 minus a2. Yeah. So if you subtract from x2 to x2 minus a2, you will get precisely minus x2 plus a2. Yeah. So this operation is same as TA times R. Yeah. So that proves that this is a glide rate. So we are reflecting along this line x2 equals a2 over 0, and adding a vector which is parallel. A10 is a vector parallel to it. Yeah, we are adding this a vector parallel. So it is a glide reflection. TA times R is it's the same as TA times. Maybe same as Q times R, and hence a glide reflection. And hence, also maybe more precisely, hence TA times R is a glide reflection. Yeah, because the other thing is, so we showed that this glide reflection is same as TA times R. Yeah, so hence TA times R is a glide reflection. So that completes the proof of this result. Yeah. So anything is either a reflection about any orientation reversing is either a reflection about a line L or a glide reflection. Is that okay? Any questions or comments? So there are interesting consequences of these things. One second. So there are interesting consequences of. So we already saw one in the orientation reversing ones. So that orientation preserving ones, that rotation along two different points is also either a translation or some rotation along about some point. Yeah. Now think about what is reflection. Yeah. So if I do, or rather, think about so say one consequence is say R1 or rather, yeah. So maybe let's call it M1 and M2 are reflections about line L1 and L2 respectively. Yeah. So say M1 and M2 are reflection about the line L1 and L2 respectively. Yeah. So if I consider M1 composed M2, yeah, what kind of isometry is M1 composed M2? So M1 is orientation reversing, yeah, and so is M2. So what is M1 composed M2? It's orientation preserving, right? So what it tells you is that it has to land in this category. It's either rotation of a plane by an angle theta about some point, or it is a translation. Yeah. So what do you think it will be?
Rotation.
So it depends upon the lines actually. Yeah. So say L1 and L2 are so it will be mostly rotation. That is right. Yeah. So say L1 and L2 are not parallel lines. Yeah. So say L1 and L2 not parallel, which is most of the time. Yeah. Then they intersect at one point. Yeah. So let P equals the point L1 intersection L2. Yeah. So then, of course, M2 fixes P and M1 also fixes P, right? So this M1 composed M2 will fix P. And since it's orientation preserving and it fixes a point, then it has to be a rotation, right? Because so either it's a translation or rotation about some point. And translation doesn't fix any point. So it must be a rotation. Hence, M1 composed M2 fixes P, and it is, and hence it is, no, so rather this is obvious M1 and hence it is rotation about. Yeah, so this is what we saw last time, that anything which fixes a point, any orientation preserving isometry which fixes a point has to be a rotation. Yeah. And what happens if L1 and L2 are parallel? So that you can imagine, yeah. Then you are reflecting by reflecting about two parallel lines. Then this will lead to a translation. So L1 and L2 are parallel. Then, so for instance, say x1 axis and x1 equals and x2 equals some 3. Yeah. So this and this x1 axis and 3 units up parallel to the x1 axis. Yeah. So if you do the reflection about these two, then M1 composed M2 is translation by a vector, which is by what kind of vector will it be? Can you specify the direction of the vector? So if you reflect by L1 and L2 and both are parallel, then this will be a translation by which direction? So say x1 axis and something by parallel to x1 axis. So you can check that the x1 coordinate will not change in that case, yeah, of any point. Only the x2 coordinate changes, yeah. So that tells you that it has to be in the direction perpendicular to this x1 axis, yeah. So by a vector perpendicular to L1 or L2. So because they have the same direction, it. Any questions? No, is that clear? Yeah. Okay, good. So there are some similar. You can do some combinations and so on, and get some similar interesting results, which geometrically seems yeah, somewhat surprising. That if you do reflection about x-axis and then by y-axis is actually a rotation. Yeah, about some point about the origin, for instance. Yeah. Okay, so now we will study finite groups of finite subgroups of this group M of all isometries of R2. Yeah. So today we'll study this, and then I don't know. Next time we will we'll do something. Oh, let's see how far we go. Yeah. So we want to know what are finite subgroups of isometries of M. Yeah. So before that, let's just try to understand finite subgroups of isometries which fixes origin. Yeah, which we remember are orthogonal groups. Yeah. So these are 2 by 2 matrices which are orthogonal. Yeah. So let G be a finite group. So important word is missing. G subgroup of O2 be finite. Yeah, so it's okay. So this is a notation for subgroup. Less than equal to means subgroup. Huh? So let me just write it. Then G is cyclic group of order n, where so it is some cyclic group of order n, or it is isomorphic to the dihedral group. So have you seen this? So you have seen some group theory, right? So you know what a cyclic group of order n is, yeah? It's isomorphic to Z mod nz, if you like. And you know what dihedral group is? Yeah, everyone? Is there anyone who doesn't know what dihedral group is? Okay. So I suppose you know what dihedral group is. It's sort of symmetries of a n-gon. Yeah. So a polygon with n sides, if you a regular polygon of n sides, if you look at the symmetries of that is what D2n is. Yeah. So it has this representation. It has an element of order n, an element of order 2, and it's not a commutative group, so there is a relation that AB is not BA but BA inverse. Yeah. So you can, this is sort of called the representation of dihedral group. So it has exactly 2n elements, a square up to a power n, and then ab, a square b. So the set is basically, so if you know dihedral groups, so then you would know that these are the elements of it. So on. A power n. A power n is same as identity. So maybe I can write b here. And maybe a power n minus 1 and identity. Okay. So these are the, so that there are 2n elements, and these are all the 2n elements. Yeah. So if you multiply these together, then a product of any two of this kind will, again, using this AB equals AB inverse, you can rewrite it in this form. Yeah. And remember, BA inverse is same as B a power n minus 1. Yeah. A inverse is a power n minus 1. Okay. So we want to show that any subgroup of finite subgroup of the orthogonal group is one of these two forms. Yeah. So let's look at elements of G. Suppose every element of G is orientation preserving. Yeah. So in this case, we will show that it is a cyclic group of order n for some n, and otherwise, we will, if it contains, if every element is not orientation preserving, that means it will contain a reflection, and in that case, we will show that it will be D2n for some n. Okay. So suppose if every element of G is orientation preserving, then what does it mean? O2, so all O2 consists of, everything is orientation preserving. That means it's all rotations. Yeah, there is no translation, obviously. So it's all rotations. So every element of G is a rotation by some angle. Yeah, it could be the identity element is rotation by angle 0. Yeah, so every element of G is a rotation by some angle. So what you do is, G will contain some rho theta 1 to rho theta n. Yeah. So what you do is you let rho theta to be something different from identity with theta greater than 0 and the smallest of these angles. Yeah. So of course, maybe this you can assume is identity, and then you can order these theta 2 to theta n, you can order it. It will be some positive angles. So you take theta to be such that is the smallest of the theta 2 to theta n. Yeah. So then rho theta belongs to G, and it is smallest among these theta 2. So smallest angle among, let's say in this notation, is theta 2 to theta n. Okay. And so we are assuming that the size of order is size of G is n. Yeah. So n is maybe the right way to write it. Where n is order of G. Yeah. So what I want to what we will show is that theta is going to be 2 pi over n, and hence G will, and of course then rho theta is changing the angle by 2 pi, rotation by 2 pi over n. And so if you square it, it will become 4 pi over n, 6 pi over n, and so on, up to when it becomes 2 pi. Yeah, these are all going to be different angles. So, I mean, what I'm trying to show is that, is that rho 2 pi, so rho 2 pi over n, the order of this is precisely n. If you compose it n times, then you get rotation by 2 pi, which is same as the identity. Yeah. Is that okay? So once we show that theta equals 2 pi over n, then we get that G is a cyclic group of order n. Yeah, it's generated by only one element. So so let's see why this is true. So first of all, we are taking theta to be rho theta to be an element of G, and order of G is n. Yeah. So if I raised rho theta by nth power, then I'll get identity. Yeah, because order of this element. So this you know, right? Rho theta, if I compose it n times, where n is the order of the group, then it has to be identity, right? I mean, this is saying that if you take an element G in G, then the order of take an element X in G, then the order of X divides the order of G, right? So this is something you have you seen these results, basic results? Yeah, so have you seen this? I mean, you'll have to answer, otherwise I have no way to guess. If X belongs to, so what I'm using is if X belongs to G, then order of X. You know what order of X is, yeah? Yes. Order of X divides order of G. This you know? Yeah? Yes. Okay. So that is what I'm using to say that if I take the nth power of rho theta, then this has to be identity. But what is nth power of rho theta? We are changing, we are rotating by, if you do once rho theta, it's changing the angle by theta. If you do it n times, then it's rotating by the angle n times theta. Yeah. So that tells you that n theta is uh, uh, n theta is same as a multiple of 2 pi because this is identity. Rho n theta is identity. That tells you that n theta has to be a multiple of 2 pi. And remember, theta is some angle less than 2 pi. All these theta 1 to theta n are angle less than 2 pi. So m has to be less than n as well. Yeah. So theta, what you get is theta is 2 pi m over n, yeah, for some m. So we'll have to show m is actually 1, but so far we have only shown that theta is 2 pi m over n, yeah. Now let theta prime be such that g theta prime is in G, yeah. So theta prime is some other element of the set, yeah, theta 2 to theta n. So again, again by the same logic, if we compose rho theta prime n times, then we will again get identity because it's an element of G. So that tells you that theta prime is also 2 pi m prime over n, where m prime is again some number less than n, but it has to be greater than m, yeah, because theta is the smallest, yeah. So that tells you that theta prime is 2 pi over m prime over n, where where m prime is some number smaller than m. Yeah. So now look at this composition. Rho theta prime composed rho theta inverse. Yeah, I've written minus k, but pretend minus 1 for the time being. Yeah. So then this is yeah. So then this is rho theta prime. So right now let's just assume it's minus 1. Then this is just rho theta prime minus rho theta, yeah, because rho theta inverse means you are rotating in the other direction by minus theta, yeah, and then adding theta prime. So it will be some positive angle, yeah, and that positive angle is theta prime minus theta, right? So so what you get is minus m, yeah, over pi, because theta prime is 2 pi m prime over n and theta is 2 pi m, yeah. But this guy theta rho theta prime and rho theta inverse, they both belong to G, so their product belongs to G. So this belongs to G, yeah. And by minimality of theta, that tells you that this m prime minus m has to be again at least m, yeah. And you can repeat it with various k. You get this, yeah. So these multiples m prime minus km, this can't become smaller than m, yeah. if it becomes smaller than m, it must become 0 or negative, right? It can't be between 0 and m strictly, right? Because theta is the smallest. So since theta is smallest, that tells you that m prime has to be a multiple of m. Yeah, is that okay? So you keep decreasing by you keep decreasing m prime by m one at a time. So you subtract m, again subtract m, and so on. If if it comes in the range 0 and m, that means something is wrong. Yeah, we have found some angle, some element of G which does the rotation by an angle theta, which is some rotation by an angle alpha, which is strictly less than theta. Yeah, so that can't happen. So that tells you that eventually you'll, when you keep doing it, it will become m prime will become equal to km. Yeah. So m prime is a multiple of m. Is this okay? This argument? Yeah. So that tells you that rho theta prime is just rho theta power k. Some rho theta prime is a is is a power of uh, is a is a power of rho theta. Yeah, if m prime is a multiple I, so I m prime is equal to m times k. Yeah, so then rho theta prime is just rho theta applied k times. Yeah, because theta prime is 2 pi mk now. Yeah. So that tells you that every element of G, so I had taken rho theta prime to be an arbitrary element of G. Yeah. So we see that every element of G is a power of rho theta, and hence G is a cyclic group. Yeah. So G is generated by just rho theta itself. And since G has order n, what we get is that theta has to be 2 pi over n. Yeah, it can't be anything else. Yeah. Is that okay? So I mean, a priori it says that theta has to be 2 pi m over n, but m, I mean, if the order of G is n, then m has to be co-prime to n, but then you use again the minimality of theta, and then you will argue that it can't be, it has to be 2 pi over n. Yeah, it can't be anything else. Okay. So that proves that theta is 2 pi over n, and G is, and we have already proved that G is generated by rho theta. Yeah, so it's already cyclic. Okay, so this does the case when G every element of G is orientation preserving. Then it must be and this finite group must be of generated by rho 2 pi over n. Now assume G contains a reflection. Okay. So in this case, what we'll do is we'll look at the subset, or in fact, you look at all elements of G which are rotations. Yeah. So identity, for instance, you think of it as rotation by angle 0, and you consider the set of all rotations in G. Yeah. So it's a non-empty set which contains identity, and composition of two rotation is also a rotation. Yeah. So it is a subgroup of of G. Yeah. Okay. Yeah. But before that, so by first of all, it contains a reflection. Yeah. So along some line L. Yeah. So suppose G contains a reflection about a line L. So now by changing basis, we can make sure that changing the basis of the plane, we can assume that R is a reflection about x1 axis. Yeah. So even if it so say it is a reflection by this line L, then what we'll do is we'll change the basis of, from this x1 x2 to this and something perpendicular to this. So this R contains a reflection R. by choosing appropriate basis, we may, so maybe R, so we have chosen it to be a reflection by x-axis. So let's not give this name an R. Some reflection, reflection about the L-axis. By choosing the appropriate basis, we can assume that that reflection is R. Yeah. Now let G. Um, um, yeah. So remember G is so now you take H to be G to H to be those elements of, so remember G is subgroup of O2. Yeah. So it contains some rotations, some reflections, and so on. So you consider this set, and as I said, this is a subgroup of G. Yeah. Because composition of are you still with me? Yeah. Can you hear me? Yeah. Okay. So as you can see, H is a subgroup of G because it contains identity, and composition of two rotation is rotation. Yeah. So by previous part, we know that H is a subgroup of O2 which contains only rotations. Yeah. So H must be cyclic group of some order. Let's say it's a cyclic group of order n. So by previous part, by case one. Yeah. We get that H is given by is generated by rho theta, where theta is 2 pi over n, and where n is the order of H. Yeah. So now we will show that G is actually isomorphic, is equal to rho theta. Rho is this group. Yeah. So this, remember, is D2n. Yeah, so the element of order 2n. So of course, this rotation by angle 2 pi over n and reflection. This is precisely isometries of a n-gon. Yeah, hence it is D2n. Yeah, so we want to prove that G is precisely equal to is isomorphic to D2n. Yeah. So in fact, we will show that G is actually equal to this, which is isomorphic to D2n. Yeah. So of course G contains H. Yeah. So it contains rho theta square, rho theta power n. Yeah. And G also contains R. By our assumption, it contains the reflection. So it contains rho theta R, rho theta R, sorry, the square is rho theta square R, and so on, rho theta power n R. Yeah. So we already know that the right hand side is contained in the left hand side, which is same as G. Yeah. So let's just write G here. So the right hand side is of course contained in G. We only have to show the other inclusion. Every element of G is of this form, is what we have to show. Yeah. So take any element of G. Yeah. So G is a subgroup of O2, right? So it's either a rotation or a reflection, or a rotation followed by reflection, or reflection followed by rotation. Yeah. So it's either, there is no translation. So what we know is that G is either rho alpha R or rho alpha for some alpha, some angle alpha. Yeah. This is what we know about any element of G. Now, if G is rho alpha, then of course it's a rotation, right? So it automatically belongs to H, and hence it belongs to right hand side. Yeah, because H is contained in the right hand side. It's actually one of these rho theta or rho theta square or rho theta power I, some power of rho theta. And if now consider the case G equals rho alpha R. Yeah. So if G is rho alpha R, what you do is consider G times R. Yeah. What is G times R? Is rho alpha R times R, which is rho alpha, right? Because R has order 2, right? It's reflection. So R square is 1. So it is rho alpha. So it automatically belongs to H because again it's a rotation. Yeah. Hence we see that rho alpha, which is GR, is is going to be, I don't know. So I've written it in a somewhat funny way. So maybe I should write it 2 pi over n for k for some k. Yeah. Which is same as so 2 pi n theta was 2 pi over n. Yeah. So I g theta is so that tells you that and now you multiply both sides by r. So you get that g is so where theta is where we call theta is 2 pi over n. Yeah, so you multiply r on the right on both sides of this equation, then you get that g is rho theta power k times r, which is one of these guys. Is that okay? Yes, so this completes the proof that every finite subgroup of O2 is indeed either the cyclic group or D2N. You can't get anything else. Yeah. So next, in fact, this is true about finite subgroups of M as well, but it requires a little more argument. See, the point is, I mean, M need not fix origin. Yeah, so elements of M may not. It may be some other rotations and so on. Yeah, but what we'll show is that even if we take any finite subgroup of M, it is going to be isomorphic to either cyclic group or dihedral. Yeah. So in fact, what we'll show is that if we take a finite subgroup of M, every element of that group fixes some point. Yeah. So if once we prove that, then we can do we can change our we can take that point to be the origin. Yeah. And then think of elements of G as elements of the orthogonal group of that plane, yeah, where that plane has origin at that point, and hence we get this. So for that, I need some I need to develop a little more theory, so some group action, yeah. So one can do it in a more brief way, but anyway, we'll need group action, so I'll do it in somewhat elaborate way. Yeah, so let's discuss group action, and then we'll come back to this question. Okay. Yeah. So let's talk about group actions. Okay, so have you seen group actions? Some of you, how many of you have seen group actions? How many of you haven't seen group actions? Oh, so everyone has seen some bit of group action. Yeah? So what is a group action? So so maybe let G be a group and S be a set. So what is group action? So group action means G acts on this set S. So the way to denote it is by this function. So group action, the act, or rather maybe a function A, let's call it, from G cross S to S is called left group action. So there is something similar to left group action, which is right group action, but left group action. So I'll ignore the word left in future if the following holds. So there has to be some axioms, like group axiom. There is an axiom for group action. Yeah, one. Um, so A G1 A E comma S is equal to S for all little s in capital S. Yeah, maybe I should write. Yeah, it's okay. Okay, and so this is the first condition. So identity sort of fixes everything. So usually it is written this A G comma S is or A X. So I'll use the word X so that is sort of is usually denoted by X dot S. Yeah, for X in G and S in. Okay, so we will so the group this function AES is denoted this. So you drop the function name as such, yeah, and use this as your notation. So I, if you use this notation, then what it's saying is that ES is same as S. Yeah. So identity doesn't do anything on S. Second is that A, so it behaves well with respect to group operation. A X1 S, and then you again apply. So it will be an element of S, and then you do X2 S. This is same as A X2 X1. Yeah, sorry. A X2 X1 comma S. Yeah. So it looks, I mean, if you have seen group action, it may look somewhat clumsy, but in the other notation, what it says is that X2 dot X1 dot S is same as you first multiply X2 X1 in the group and then do S. Okay. So this is it's acting on the left. So I mean, we are using this left notation. So if you do right action, then somewhat similar, but it should and then it changes. Yeah, this axiom changes for left action and right action. Okay, so this is so if it satisfies these two properties, then you say that this is a group action. Yeah. So so a group action is just such a function. Yeah. So what is an example of a group action? So let's just see some. So we have already seen many group action. It's just that um, yeah. So we may not have explicitly realized it. So for instance, this M set of isometries of plane. This acts on the plane. Yeah. So what it does is M comma the vector A goes to MA. Yeah. So this is M acts on R2, right? So this is indeed an action. So we know that if we compose these two and so it the is this okay? Yeah, that this is an action. So it does fit into what we are talking about. Or even if you look at linear maps, linear maps are given by matrices. Yeah, so matrices acts on the vector Rn. Square matrices n cross n matrices acts on the vector Rn. Yeah, so but this is not a group, but um, so this is sort of GLN. Yeah. GLN is a GLN of a field, or let's say R. This acts on Rn. Yeah. So A comma V goes to AV. Yeah. So this is again an action because um, B A V is same as B A V. So the second axiom is true by this identity because my matrix multiplication is associative. Yeah. And the first axiom is also true because the identity doesn't change anything. Here also, if you take the identity element of M, then M it preserves A. Yeah. So these are some examples of group action. One more example, which if you have seen group action, then you must have seen this. Let S equals G itself. Yeah. And consider the action G cross S to S. So what you do is X comma S, you send it to X times S. Yeah. X times S makes sense because S is also G. Yeah. So it's an element of S again, and this is again an action. Yeah, because note ES goes to E times S, but E is identity element, so it goes to S. Yeah, for all S in S. Yeah, and of course multiplication is associative. So G1, G2, S. It doesn't matter which way you do it. Yeah, the same as G1, G2. Yeah. So that tells you that this is also an action. Yeah. So there are many examples of an action. Yeah. So now I guess I can't make it any smaller, but yeah. So now there are some words about some terminology for this action. Yeah. So um, let me introduce that. So mm, uh, so first of all, I if G acts, if a group G acts on a set S, then we say S is a G set. So it's a shorthand for saying that G acts on a set S. Yeah, that is S is a G set. So this is more like a notation. Also, let S be a G set. That means G acts on a set S. Let little s be an element of capital S. Yeah. Then then the set GS. So it's denoted by GS. G times S, small g in capital G. This is called, what is it called? Called the G orbit of S, of little s, or simply orbit of S. Yeah. So if G is understood, there are not two groups involved, then just orbit of S. Yeah. So all the points where S can go under this action the set of all points where S can go in this subset, that set is called the orbit of S. Yeah. Is that okay? And then there is a, so this maybe I can underline. And something called the stabilizer. Okay. So that the stabilizer of S. So maybe the right way to, I want to write it in a, let S be in S, the stabilizer of S, denoted by stab S, is the set G in G, G in G, such that GS equals S. Yeah. So of course, stabilizer is non-empty. Why is it non-empty? Identity belongs there. Yeah. So in fact, this is a subgroup of G. Yeah, because it's non-empty, and if G and G prime fixes S, then their product also fixes S. Yeah. So it is a subgroup of G. Orbit by definition is also non-empty, right? Because S belongs to its orbit. Right? Identity will send S to itself. But it may happen that it is just a singleton set, or it may happen that it's the whole thing. Yeah, so everything is possible for orbit. Okay. Okay, so let's get back to, so there's more to do in group actions, but we'll do that in a bit. Let's just finish off this thing, finite subgroups of M. Okay. So, okay, so maybe I'll write it here. Yeah, maybe this is good. So let's just move it here so that it doesn't, when I'm copy pasting it, it doesn't interfere. Okay, so, yeah, that's not good. Okay, so let G be a finite subgroup of M. Yeah, so M is the group of all isometries. Yeah. Then what I'm trying to, then what we want to show is, maybe let's call it a proposition. Yeah. And from this, it will follow that. Then there exists a point P in R2, which is fixed by every element of G. Yeah. So G basically fixes one particular point of the plane. That is what we want to show if G is a finite group. Okay. So proof. So let's give elements of G some name. Yeah, G1 to Gn. One of them is identity, but maybe we don't need that. Yeah. So So it has some order, and let these be the elements of G. Yeah. So now what I'll do is so we know that G acts on R2, yeah, every on the whole of R2. But if I look at whole of R2, it's a bit messy, yeah. So let me start with looking at some point first, yeah. So let S be a point in R2, S be some element of R2, yeah. Okay, and then let S equals. So what we do is we look at the orbit of S. Yeah. So let S equals GS. So and this is what G1S to GNS. Okay. So this is S1 to Sn. So I mean, but it's not clear whether they are all same or distinct or whatever. Yeah. So it may not have n elements. I mean, for instance, we are trying to prove that there exist a points which is fixed by all GI. So if I chose S to be that P, then it may be just one element. Yeah. But it doesn't matter. It has some number of elements. But okay, let's not worry about this. Yeah, so let's just call it this thing. Yeah, so I can call it as, let's just keep it as it is, S1 to Sn. Yeah, so SIs may not be distinct. Be distinct. Yeah, so it may not have endpoints, but GIS, we will call it SI. Yeah, so it may happen that S1 and S2 are same. But the point is G acts on S. Yeah, this part is okay, right? Why? Because so note that G, so I mean S is a subset of R2, and so G acts on whole of R2, but it also acts on the subset, meaning it. So G acts on S. What I want to say is G permutes the elements of S. Yeah. So maybe that is a better way to write. G permutes the elements of S. Yeah. Why? Because if you think about it, uh, uh, let G be in G, then what happens to GS1? Then look at GS1 to GSN. This is just G1S to GNS. Yeah. But yeah, so maybe I should have said so. But what happens to GG1 and to GGN? It's just a permutation of GIs. Yeah. So note that G action on G. So not that. Yeah, maybe this is straightforward. So G1, this list to GGN is a permutation of G1 to G. Yeah. Because, I mean, so maybe this is a good exercise. So what we are saying is that this action which we defined here, this example 3, this this action, it permutes the elements of so it doesn't fix anything. Yeah, it permutes the elements of S. Yeah, this in this example. Yeah, so maybe I'll just. So this is just basics of group theory. I mean, this follows from the first principles of group theory. It's not. Where did it go? Yeah. This is yeah. So it's a permutation of. So maybe you can think of it as an exercise or a homework. I'll think about it further too. So it is a permutation of G1 to Gn. So hence G1 S to GNS is a permutation of S1 to Sn. Okay. Is that okay? Yeah. So now, actually, maybe I should have chosen. It would have been. I mean, one can choose an S such that all its I mean, all these SIs are all distinct. I mean, in fact, most tests will do that, but maybe it's not needed. Yeah. So, um, so what you do is consider let P be. So these SIs are elements of R2. Yeah. So you take P to be S1 plus S2 plus Sn over N. Yeah, as an element of R2. Yeah. So now the claim is that this point P is preserved by all the G action. Yeah. Okay. G P is equal to P for all G in G. Okay. So why is that? So basically, the point is this set and this set doesn't change. Yeah. So GP is equal to GS1 plus GS2 plus GSN. But this is a permutation of S1 to Sn by N. Yeah. So this is same as S1 plus Sn by N. Yeah. Which is yeah, there is some problem. So this is true, but I need a little more justification. Yeah. And think this through. Yeah, there's some question in this. Yeah, so maybe this question I can answer easily. So this is a permutation of G1 to GGN is a permutation of G1 to GN. Yeah, that part you agree, right? So this is going to be G sigma 1 to G sigma N for some sigma, a permutation from N to N, yeah? A sigma in Sn, if you like, the permutation of n elements. Right, and then so if you think of so so this set is precisely then S sigma 1 till S sigma 1 to S sigma n. Yeah, because G sigma 1, what will it do? It will send S to S sigma 1, yeah, by definition. Yeah, so this is what the definition S sub GIS is precisely S sub I. Yeah, so this hence hence this is a permutation of S1 to Sn. Okay, but problem is I mean I don't know why this G preserves addition and so on. Yeah, so it is it's not a linear. I mean G is some element of this group G, so it's not necessarily a linear map. So that's why I can't write this formula. But this is true. So there is something. So one has to give a justification. Is that? But I hope this is clear that G that part is a permutation. I hope is now clear. But so there is a lemma. Okay, in the book there is some lemma. Okay, so maybe this lemma I'll prove later. Yeah, let me just conclude the argument here, and uh, yeah, and then I'll come to this lemma. So there is some detail which was missing. Yeah, so the lemma is isometries. So see this P is a centroid of note that P is the centroid. So average of S1 to Sn, which is called the centroid of S1 to Sn. And so the lemma says that isometries preserve centroid. Yeah, so take centroid to centroid. So lemma says that isometries take centroid to centroid. Centroid. So what it means is that if M is an element of M, which is an isometry, and then centroid of S1 to Sn, then maybe P, which is the centroid. So let's write it this way. Then MP is the centroid of M S1 to MSN. So let's assume this lemma, and from this lemma we will. So what it says is that the centroid of S1 to Sn is when you apply M to it, it becomes the centroid of MS1 to MSN. Yeah. So now, if you think about it, so let's just erase this part. Yeah. So now you take let G be in let G be in G, then then GS1 to GSN is again, since it's a permutation of S1 to Sn, it's again S1 to Sn, and hence by lemma, GP is the centroid the centroid of S1 to Sn, is the centroid of GS1 to Sn, but that is same as is the centroid of S1 to Sn, I P. So GP is same as P. So that completes the proof. Hence the proposition. Okay, so we got this proposition. So I'll come to lemma in a bit. Yeah. So let me just finish the main theorem that any finite subgroup of M is isomorphic to Sn. So now theorem. So I'll complete the proof of this lemma. So once I prove this lemma, everything will be done. Yeah. So I skipped this lemma in the textbook. That's why I got stuck. Yeah. So now this theorem is that G subgroup of M is finite, then G is isomorphic to is either cyclic, group or dihedral. Yeah. So proof. So by previous proposition, there exists P in R2 such that G fixes P. Yeah. Fixes this element P. Right. So now I mean, it's a plane, right? So you think of you pretend that P is origin. Yeah. So you choose your coordinate axis such that P becomes origin. Yeah. So P is some point here. Now you pretend that this is your coordinate axis. Yeah. So you choose this as your coordinate axis. then G, I mean, anyway, it's a symmetry of anything which is distance preserving for this coordinate axis is also distance preserving for this. So M is sort of coordinate free, right? So we can take whatever coordinate system. Yeah. So by previous now choose coordinates of the plane so that P is the origin in these new coordinates. Yeah. So in these new coordinates, P is the origin. Yeah. So now what happens is G is a subgroup of these of this of M, but it fixes the origin. So G then G is the subgroup of isometries which fixes origin with respect to the new coordinates. Yeah. So then, I mean, with respect to this new coordinates, this G is a subgroup of O2. Yeah, with respect, hence G is a finite subgroup of O2. And hence the result follows from from um, the previous and from the result about finite subgroups of. Okay. Yeah. So the only thing remaining is the lemma, and yeah. So I didn't see. So let me just see if the proof is straightforward. Yeah. So one has to do a few some cases. Yeah. Yeah. So it is. So it is okay. Yeah. Um, so of course. Yeah, so let me just, so this lemma is also pretty straightforward, yeah. So for linear maps, we know, so that is what I was trying to apply, but for translations, we don't know. Yeah, so proof of lemma. Yeah, so, yeah, so this is the lemma. We want to say that centroid goes to centroid, yeah. So under any element of M. So let M be in M. Yeah, so how does M look like? M is some TA times some linear TA compose rho theta compose R, or TA times some phi where phi is linear. Yeah, linear map. Right. So of course, phi of P is P of S1 to Sn over N. yeah, which is same as phi of S1 up to phi of Sn over n by linearity. So this is by linearity. Hence, phi p, hence phi p is the centroid of phi S1 to Sn. Yeah. So for linear maps, it's okay. So all we have to do is show this for translation. Yeah. So if this is true for linear map and translation, then it is true for the composition as well. Yeah. So now for translation, TA of P. What is T of P? Is just P plus A. Yeah. And so we want to show that P plus A is actually centroid of TA of S1 to Sn. Yeah. But P plus A is what? It is, you can think of it as, I don't know what happened. Okay, no. So P plus A is simply, um, P is, so S1 plus Sn over N plus A. Yeah, but I can write it as S1 plus A plus S2 plus A plus Sn plus A over N. Yeah, because N and N will cancel out and you'll get A. Yeah, but this is precisely TA of S1 plus TA of Sn over N. Yeah, because this is the translation. Yeah, so that tells you that TA of P is the centroid of TAS1 TS. Yeah, hence it works with hence it works with composition as well. Yeah? TA compose phi of P is the centroid of these things of TA P. That's what. Okay, so that finishes the discussion which we wanted to do today. Yeah, all finite groups of M. Okay, any questions or comments? Okay, good. So I guess we couldn't do anything further. So we will, yeah. So anyway, Wednesday I'm there. So we will need some more. So I thought this chapter 6 will not take too long, but I mean these are some interesting geometric results, so it's taking too long. But so maybe on Wednesday again we'll go over this symmetries a little more, and we will start. Yeah, so maybe in following Monday we will wrap up group theory. I was hoping that we'll wrap up group theory Wednesday, and then Monday and Wednesday we'll do some spectral theory, but we'll start spectral theorem discussion to also, but looks unlikely. Okay, maybe first I should